is calling you. The universe is calling me. It speaks both day and night. It's full of dark and light.
Hello and welcome to SkyTour Radio here on KGRAradio.com. I'm your host, Mark D'Antonio, here with my astonishing co-host, Amanda Curran. Hello, Amanda.
Hi, Mark. How are you?
I am fine, thank you. And hello to our KGRA broadcast listeners, the most wonderful audience on the planet. Now, a few quick announcements. And before I get going, I just want to do a quick shout out to Rennie, Shelley, and Jody down in Florida and who are tuning in along with thousands of others around the country. And if you want to get on a shout-out list, just send us an email, and we will be happy to add you to our shout-out list. So please do subscribe if you want to our companion stream to the SkyTour Radio, which is SkyTour Livestream, and that's on YouTube. And on SkyTour Livestream, we take you on a clear night journey to the deep sky, and where you learn about deep sky objects and you see them in real time with very sensitive telescopes in a professional observatory setting. So see the universe as never before on SkyTour Livestream. And the journeys will resume in just actually coming up on just a few days from now. So while there, don't forget to click the bell to get notified about any of our events. And lastly, make sure you visit our online store at fxmodels.com or at the FX Models Planetary Replicas page on Facebook, where you can purchase Moon, Mars, and Pluto swag. And if KGRA listeners enter the code ST15 during the checkout, they'll get a $15 discount. This is exclusively for the KGRA listeners. So the links are on the SkyTour Radio page, or you can jump into the store at fxmodels.com, or again, the Planetary Replicas page. Now, tonight on SkyTour Radio, first we're going to start with an exoplanet roundup, and we're going to discuss the latest exoplanet finds. And we're also going to ask, as we did last week, could alien life exist on any of these planets that we're talking about? And if so, what would they look like? Then we're going to talk about star catalogs. Well, in a sense, we're going to talk about how we name stars and why we call them such. And this will be something to help you along as we move further into our series. So the question becomes, how do we know which stars go in which catalog? And we'll answer all those questions. Now, the next thing we're going to talk about is how bright are the stars? We're going to talk about how astronomers classify stars by brightness. Now, we already know that they classify them by color for their spectral type. And that's that OBAF-GKM thing we've talked about several times. But we're going to do all this in a simple and understandable way. So, first up, last week we saw Kepler 452, which was a star that was identified by the Kepler Space Telescope that had 3 exoplanets in the habitable zone around that star. Now, that habitable zone, remember, is the place where liquid water could exist. They say that not too hot, not too cold. Well, what they really mean is where liquid water could exist on the surface. That means an ocean. And of course, oceans to us mean everything. Your body is salty. If you lick your forearm, you'll taste salt. And the reason goes all the way back to when we finally left the water as a species. Well, that was a long time ago now, wasn't it? Certainly wasn't last week. And that salinity in your body is a direct offshoot of removing ourselves from the ocean. We actually carried a vestigial ocean with us in something called the skin. And so we carry a little ocean with us at all times. And that's, I think, a really cool, fun fact. Now, those 3 exoplanets in that habitable zone around Kepler 452, they all might be what we call super Earths. Now, what is a super Earth? You've heard the phrase before, I'm sure. A super Earth is greater in mass than our Earth, but less in mass than Uranus, okay? What does that mean? It means between 1.1, say, and 15 Earth masses. So anything in there could be a super Earth. And it's also possible that the planet could be rocky, a giant Earth, basically. All right, and that's why we have to say it could be a super Earth. It could also be a planet like Uranus, a gas giant, but, further study can show us that. all right? Because we can detect what we call puffy atmospheres around these exoplanets. And if we can do that, then we can tell whether the planet might be a terrestrial planet like the Earth with a thin shell of atmosphere like we have, or a big heavy atmosphere like that of Jupiter, Saturn, Uranus, and Neptune. So that's very interesting. Now, we saw that was 452 that we're talking about. Now, there were another 3 planets that were discovered back in 2015, but these are much closer to the star, and they're given the designation of B, C, and D, all right? And D has an orbital period, that is to say its year, of only 24 days. So if you're thinking about TRAPPIST-1, that system we talked about in the past, well, then you'd be right. It's sort of like that. So it's kind of odd having a planet that has an orbital period that is a year of 1 month. I mean, that would throw anybody for a loop, right? You know, just for a month, it's a year goes by in 1 month. Blah, that's crazy. Now, the star is called HD 7924. Now, the HD stands for Henry Draper, who was an astronomer, and he created this catalog. Now, we're going to talk about that shortly. The star is 55 light years away. That's relatively close, you know. We consider it close. And at our fastest speed, it would still take us 153,488 years, yes, I calculated it, to get there. So why do we care? I'll tell you why. Now, the planets are not habitable in any regard because they're way too close to the star. So they're all scorching, okay? So, but this 55 light year distance gives us something else that we can do. And I'm going to talk about that in a moment. Now, let's go to the next find in our exoplanet roundup, GJ9827. That's the designation for this star. This one's about 100 light years from the Earth. The previous one was 55 light years. This is about 100. It has 3 transiting planets that we can see from Earth. That means the planets pass between the star and us from our perspective. And we can see that happen. And as it does, as each planet passes in front of its star, it generates a light curve, meaning the starlight drops just a little bit. And that dip in the starlight is what we see. And that is the main thing that the Kepler Space Telescope was looking for. And then after the Kepler had a problem, they re-engineered the Kepler when it was out in its orbit and managed to bring it back to life. And that was the K2 mission, the additional mission that Kepler did and still does. So we can see these generated light curves like this. And this basically, when we see a light curve like that, it tells us many things. We can, with confirmation of this as a planet, we can find the planet's mass, find the radius of the planet, and find how fast it goes around the star. Now, armed with that data and the data on the star itself, this provides a tremendous overview of the entire system. And this is something that's really, really important for us. And so this is why exoplanet science is so important in general, because in effect, we're going to find our new home this way. Let's not mince words. Someday, the sun is not going to be here anymore. It's going to run out of hydrogen. It's going to swell into a red giant, as we talked a little bit in previous shows. And then that is going to swallow Mercury, Venus, and probably the Earth. Now, oddly, at that point, maybe Mars will be habitable for a few 100 million years. But then it will go, and as the star shrinks again and goes to a white dwarf, Mars will be relegated to the deep freeze once again. So the question is, what is so special about these other stars that are that HD 7924 and GJ 9827? Right? They're 55 and 100 light years away, respectively. Now, the reason that they're important is because in just a few short months, the James Webb Space Telescope is going to get launched. And guess what? When it gets up there, it's going to be able to look at these planets directly. And because of their proximity, they will be great test cases for studying planetary atmospheres around other stars with other worlds. This is going to be brand new, groundbreaking study. Fantastic stuff. And we'll get a good foundation from the study of these two systems. Now, going back a bit, you heard me mention the names of the stars, HD this and GJ that. What does all that mean? Really, here's how it works. There's many catalogs of stars. that were made by different organizations, different researchers, astronomers, and so forth. And each catalog tends to list certain stars that have certain characteristics. For instance, there's catalogs to list the normal stars that are out there, catalogs to list giant stars. And don't get me wrong, there's conglomerations of all of them too, but there are catalogs that are specific to normal stars like the sun, giant stars, variable stars, that is, stars that change their brightness periodically, because we do have these brightness variations in stars. And we will talk about those specifically in a future show when we talk about something called the cosmological distance ladder. In other words, how do we find the distance to galaxies and faraway stars? All right. Now, these catalogs that list stars are one thing, but there are also catalogs that list objects that are not singular stars, but might be things like star clusters, globular clusters, nebulae, and supernovae, which are exploded stars. So there's a lot of different catalogs. And so to talk about that, we want to talk a little bit about the different catalogs. Now, to those who are members and subscribe to the SkyTour live stream, you're going to know some of these because we've talked about them. We've used them as we've hunted for objects in the night sky. All right. So for stars only, we use many different catalogs, like I pointed out. But the ones that we use tonight are the GJ catalog, which stands for Gliese Jahrès, and that's spelled Jarei, and then the beta symbol, but it's pronounced Jahrès. Now, a German friend of mine confirmed that pronunciation just a few minutes ago. I just wanted to make sure I had it right. All right. So it's the Gliese Jahrès catalog. Now, there's the other catalog I mentioned, the one that had the HD in the front, and that's the Henry Draper catalog. Now, Henry Draper was a real fastidious astronomer, and he actually not only managed to catalog these stars, but he got their spectra. That is, he was able to break their light up into the associated colors that we see from the starlight. And that he did for 225,300 stars. And he published that between 1918 and 1924. So he did an awful lot. Now, his catalog covers the entire sky down to what we call magnitude 9. Ooh, magnitude, what's that? Well, stick around. We're going to talk about that. All right. Now, magnitude 9 is basically a brightness. All right. Now, there were additions made to the Henry Draper catalog. It's called the Henry Draper Extension, or the HDE catalog. It's not a big deal. And we originally had the Gliese catalog of nearby stars prior to the Gliese Jahrès catalog. And that was created in 1957, and it cataloged what was believed at the time to be just 915 nearby stars. Now, it was extended to create the Gliese Jahrès catalog, and it literally took the count of the nearby stars to 3,800 plus from 915. So, do you think we're getting better at what we do as astronomers? I think so. So, it gave us go ahead.
A quick question about that.
Sure.
Okay, you were saying that, we're just focusing on the HD and the GJ right now.
Yep.
And I'm just going to use the initials because I'm working on the names. You said like different companies had different catalogs compiled, and sometimes they kind of cross-referenced each other.
Yep.
Not all of these catalogs were all from the Kepler, were they?
Oh, none at all. In fact, many of the stars that you see in the sky have already been cataloged from as far back as the 1600s. Okay.
So who determines? I mean, it's all kind of free use. How do you?
Well, that's a good question. How do you determine which stars go where? Which catalogs mean more than other catalogs?
Yeah, and I'm sure you were getting there, but
no, actually I wasn't. But that's
I like the catalog system. It makes things easier.
It does, in fact. And the thing is, there's other catalogs I didn't even mention. Like there's a number of German catalogs. There's the Bonner Durchmustering, which was a catalog that I used extensively when I was getting my astronomy degree, because these stars had very well-known positions in the sky. It was a well-measured catalog. So the catalog entries for a star, for instance, they'll have the name, and they'll have the brightness that we're going to talk about shortly, and they'll have things like the distance, if known, the type of the star, if known, and we call that the spectral type, if you recall. That's the OBAF GKM, and then what's called the luminosity class that together makes the spectral type. So our sun is a G 2, number 2, and then V, 5, Roman numeral 5, G2, Roman numeral 5. Okay, G2 is the spectral class, and the Roman numeral 5 is the luminosity class, and together they make the spectral type of our sun. So, there are catalogs that will have that in there if it's known, and then they'll have other things that include things like the motion of the star in the sky per year, because nothing is at rest in the universe. You look outside, you see all the stars, and you say, oh, those are the same stars that were here 1,000 years ago. And the answer is, no, they weren't. No, they weren't. The galaxy is a dynamic place. We're orbiting the galaxy every 230 plus thousand years. 230 million years, we go around the galaxy just once. And we've done that 19 and a half times. So that gives you the idea that, our stellar neighbors that we have now are not the stellar neighbors we'll have in 10,000 years, 20,000, 100,000, a million years. It changes all the time. And if you could put it into fast motion, I think it would be incredible to watch just how the sky changes around you. You see some stars racing past us at high speed. You'll see other stars that are moving together into the distance. So I think that's a really cool aspect of all this. So that said, all right, the catalogs were born out of the need to catalog these stars and define where these stars are, what they're doing in the sky. And there's other catalogs, okay, that give us, for instance, objects and clusters of stars and nebulae, as I mentioned. All right. And one of the catalogs that our SkyTour live stream listeners are used to is the New General Catalog, or NGC. Now, those are for nebula and other astronomical objects and star clusters. And originally, when it was first created, it had about 1,000 objects. Now it's up to 7,800, nearly 7,840, okay, almost 8,000. And yeah, that's the one we use extensively in our observatory streams that we do here. Now, when we have the star that has that spectral class and that spectral type with its, OBA, FGKM, and the luminosity class of, Roman numerals 1, 2, 3, or 4, or 5, or more, that's one thing. But we also have to figure out, okay, how do we qualify and discuss the brightness of these stars? And that's actually the tricky part, because you see, all the stars we see from the Earth, we're seeing through perhaps some dust in the interstellar space, or through the center of the galaxy, or toward the center of the galaxy where there's a lot of dark matter, dark dust. When we talked about the Orion Nebula, for instance, we have seen that we actually have dark matter in the Orion Nebula, dark clouds. These are dark nebulae, and they cause what's called extinction. Okay, and that doesn't mean destruction. Okay, it just means dimming. It causes extinction of starlight that's in it. And sometimes when you look at the Orion Nebula, for instance, the famous nebula in the winter sky right now outside, if you look at that and you look at the dark nebula, you actually see that you don't have the ability to see through that dark nebula. It's dense gas and dust. All right, it's called the molecular cloud, which is something we've talked about, but we'll do it again at some point. So all we can do is gauge the apparent brightness of these stars. And that's something we call the apparent magnitude. All right. And it goes for a star or an astronomical object, because if we have an extensive nebula, we can look at its overall brightness and we call it its overall visual brightness or apparent magnitude. Now, it's not a linear relationship. Okay. It's something called a logarithmic relationship. What's that mean? It means that each magnitude, so you have a magnitude 1 star and a magnitude 2 star, which is fainter than the previous, okay? The magnitude 2 star is 2.512 times fainter than a magnitude 1. Just think of it as 2.5, okay? So each difference is 2.5. So this is because it's not a linear scale. Now, that could be confusing, all right, because the smaller number in magnitude is actually the brighter number, and we even go negative in this, okay, with magnitudes. So a negative number can be very bright. But all those numbers aside, which is confusing as heck, the best way to really understand this is to actually just look at known objects and be given their magnitudes. What are their brightnesses in terms of magnitude. Okay, let's start with one. Pick one, Amanda. Putting you right on the spot.
Pick a nebula.
No, just pick a bright object in the sky, and we can actually. What's the brightest object in the sky? Here it comes.
Well, I don't know. The sun.
Yes,
Alpha
good call.
Centauri.
Now the sun.
Sirius.
Let's
Okay.
start with the sun. We'll go to Sirius. The sun on
Pretty
this.
bright though. I did well for the 3.
Yes, you did.
Pretty bright things. Okay.
They're very bright. Yeah. The sun, okay, as an example, in this magnitude scale is minus 26.7. It's the brightest object in our sky. Okay. Now, what you didn't pick, but which is also there, it's easy to forget, is the moon. The moon is minus 12.6 in brightness in these astronomical magnitude, in the stellar magnitude scale. Venus, which is the brightest planet in the sky, is minus 4.4. All right. Sirius, which you did name, is the wintertime star, which is just to the lower left of Orion when you see it in the sky. Its brightness is the brightest star in our sky, is minus 1.4. Now, some stars are standards. Okay, we use them as standards because they have a fairly solid brightness, and they are at a particular point in the scale that means something to us. And one of those stars is the star.
Is Vega?
Yes, it is.
Yay! I'm learning, guys.
See that?
I'm really learning.
That's great. Yeah, that makes me feel good that you actually listen when we do the SkyTour live stream.
It's a lot of information, but like I said, if I can pick up a little bit each time, I think I'm doing well.
You are.
And Vega's gorgeous too.
Yeah, Vega's a beautiful white star, and its magnitude, its stellar magnitude on that scale is 0.00. Okay, and the stars are standard for us. Okay, and it's a standard for a number of reasons. The other one it's a reason for it being a standard is that star has the biggest absorption lines in the spectrum. Now, you might remember we talked about spectra of stars a little bit, but see, what happens is when a star is radiating tremendous energy, that radiation of the star is coming from its core, all right? And it's very, very hot, much hotter than the outer atmosphere of the star. The outer atmosphere, in fact, is cooler than the layers beneath it. So, as that hot radiated light is coming through that cooler gas, that cooler gas will absorb some of that energy. And that is shown and manifested in a star's spectrum as vertical dark bands. We call those absorption lines. And we're going to be talking about those at some point as well. And absorption lines have specific places where they go. For instance, calcium in a star's atmosphere will only be in a particular location. Hydrogen gas, the most prominent and the most prevalent atom in the universe is hydrogen. And hydrogen in a star's envelope, that is the outer part of a star, will also show in a very particular locations. Okay, so much so that we name different series of lines because there'll be more than one line. So there's a Balmer series, there's a Lyman series, okay, of hydrogen lines. And this, and don't worry about the names, but we'll cover that at some point. But understand that these spectral lines, these absorption lines, show up at very specific places. Now, Vega is a star we use as a standard for us because Vega has the biggest of the hydrogen Balmer lines. All right. So we see Vega, and not only is it a magnitude standard at 0.00 magnitude, but it's also got the largest hydrogen lines. In fact, when you're creating a spectrum of a star, your first target is usually Vega, if it's visible, because it's a great test for your system. All right? And so I've used Vega as a standard program star for a long time. So now, just so you understand, these magnitudes that we talked about, the sun minus 26.7, the moon minus 12.6, etc., Vega 0.0, the human eye can see to plus 6.5. Now, again, the magnitude scale is confusing, as I said, because the smaller numbers are brighter than the larger numbers. Okay, so the human eye can see to 6.5 at its best. Usually, if you're in a light polluted city, you might be able to see to 3 or 4, plus 3 or plus 4. In a dark sky, a very dark sky, you could see probably to plus 6.5. But that's not the faintest object there is. The faintest object, believe it or not, faintest objects are between plus 30 and 31 in stellar magnitude brightness. So there's a lot of the universe that we just cannot see. Now, this is just an apparent brightness. It's a brightness that has to do with how it looks just from Earth. If you were closer to that star, it would be brighter. And if you were farther away than at the Earth, it would be dimmer. So how do we make heads or tails? Well, we created a standard magnitude as well. And that standard magnitude is called the absolute magnitude. Now, that's a magnitude of a star if it was at 32.6 light years away. Why the heck would we say that? Why that number? Why not 32.9? Why not 31? Why 32.6?
This
Well,
is
we'll
why
see.
I don't get math.
Don't worry. We'll see this
Everything
short.
seems so random, yeah.
It's not random. This is
I'm
actually,
sure it's
and it
not.
may not appear like it has any order to it yet. All right. But it does, I promise. Now, what is an absolute magnitude? Again, that's the magnitude of the star if it was at 32.6 light years from our planet. Now, measuring all the stars at a similar distance or putting them at the same distance gives us a true comparison of their brightnesses between each other. It gives us a better appreciation for that. It also removes the distance between them so this direct comparison can be done, and it levels the playing field. All right. The problem with a standard magnitude like the absolute magnitude versus apparent magnitude is stars can have a high component of ultraviolet radiation. Remember those M stars we talked about? They're the ones that have a lot of planets around them. M stars love to give off ultraviolet UV radiation. All right.
And they're not called solar flares, but are they called something similar?
Well, they're stellar flares.
Stellar
'Cause
flares.
Solar applies to Sol, our sun. Did you know our sun has a
Yes.
name? Our sun's
Yes.
name is Sol, S-O-L. It's kind
And
of
we
cool.
only have one true solar system. In the
That's right.
universe.
That's right. So the stars
Yeah.
can give off this UV radiation, all right, and thus that would affect what we would see in the absolute magnitude. Why? Well, UV is not visible to us, and neither is infrared radiation, which is heat, all right? And now you might be wondering if we're going to have to go to a commercial break, and I just wanted to let you know that we are going commercial free tonight. Yay! Yeah, right. So that said, we continue. So stars can have ultraviolet and infrared radiation that they give off. And this is in the non-visible regions of the spectrum. So we have to qualify when we're talking about an absolute magnitude. We have to make sure we discuss what wavelengths we're talking about. Is it going to be the visual wavelength? Or is it going to be ultraviolet absolute magnitude, infrared? But we can do that. And when we do that, all right, and we have a really good feel for how this works. Let's just stay with the visual spectrum for now. And let's take a look at what this means for, say, our sun. The apparent magnitude of our sun, minus 26.7, shrinks to a paltry 4.77 when we go out and put the sun at this distance of 32.6 light years. So our sun is not anything special. It's actually rather ordinary, as a matter of fact. So its absolute magnitude is 4.77. Not so impressive. Betelgeuse, on the other hand, the Alpha Orionis, the brightest star in the constellation Orion, it's at the top left and it's orange, very, very prominently orange, as a matter of fact. It has an apparent magnitude, as visible from here, of 0.45. Okay, so just slightly positive. Okay, well, that's pretty bright. But its absolute magnitude would be minus 5.14. Obviously, it's got to be a lot farther away than the 32.6 light years. And it is. It's 420 light years away. So if you brought it to 32.6 light years, this standard location, it would be a lot brighter. All right. Now, it's also a lot bigger. And if you put it where the sun is, Betelgeuse would extend out past the planet Jupiter. I mean, that is unreal. That means remember, that's not just a linear line. That's a three-dimensional spherical volume of star. That is immense. And Betelgeuse is rather small on the totally large star side of things. And we're going to talk about very large stars in another program as well, because they're just crazy. Another star, all right, is Rigel. What's Rigel? Well, Rigel is the lower right star in the constellation of Orion. Orion has has Betelgeuse. Then next to it is Bellatrix. Then it has the belt of three, Alnilam, and Mintaka. And then the lower left, it has one called Saiph, Saiph. And the right one is Rigel. Well, Rigel has an apparent magnitude of 0.18. Okay. Now, it also has a distance of 773 light years. So it's a little further away than Betelgeuse at 420. All right. But if we brought Rigel to 32.6 light years, its brightness would be, the absolute magnitude would be minus 6.69. So you can see that that's way brighter than Venus. Venus is minus 4 in the sky. So Rigel and Betelgeuse are far brighter if brought to that 32.6 light years distance. Okay, what about that 32.6? What am I talking about? All right, the 32.6 light year distance has to do with something called parallax. It's the origin, it originates from the term parallax. And parallax is the measure of an angle. Now, what does that mean? Well, if you extend your arm out to full arm's length with your thumb sticking up like you're giving the thumbs up, and you close one eye, all right? This is how you do visual parallax. You close one eye, and you put your thumb over an object on the wall, and then you open that eye, you open the other eye and close that eye that you were just using. You blink your eyes. You'll see that your thumb seems to shift against the background of the farther objects, okay? Well, that's parallax in a nutshell. Closer objects will shift against the background of farther objects, okay? So you can try it. Extend your...
say, I found in reading different articles, NASA always phrases things like that. Like if there's a conjunction or if there's something you have to see, they'll say like, put your arms straight out and make a fist. That's like the measurement between Mercury and the moon or something. Or, you know, if you put your hand flat out. And I love that they phrase it like that, because that means anyone who's outside on a clear night has no excuse not to look up and try to see these things.
That's absolutely right. And in fact, being able to measure distances in the sky and so forth without having to have fancy tools is really something that, well, ancient people did. You know, in megalithic times, they actually, you know, had to do that. You know, mm-hmm. So that's something that makes sense. But let's make sure we understand. So we now know that the thumb will shift when you blink both your eyes. Now I'm going to ask you to do a substitution. Now, instead of your left and right eye, I want you to imagine that that's actually Earth's orbit from one side of its orbit to the other 6 months later, all right? And instead of your thumb and the farther wall, it's a nearby star and farther stars, okay? So that is how parallax works when we're talking about stars. I actually worked in a parallax program and you know, researched, you know, parallax stars for, you know, I think a couple of years actually. And let me tell you, it's really amazing and difficult to actually measure the position of a star in the sky. It's not easy because a star is only ever a bloated mass on a photographic sensor. It's not a point of light. It's not a completely sharp point of light. So you actually have to do an analysis of the density of the image you have. And that image has to be, you have to find the exact center. All right. And that's exactly where the star is. Any kind of little movement of the telescope will totally ruin that exposure. All right. Because it'll be a elongated blotch on a photo sensor rather than a round object. If it's perfectly round, then you can figure out where the center is and so forth. So now a parsec is something to talk about here, which comes into this. Now I said parallax is very important, and it is. So a parsec is defined as 3.26 light years. Okay, now if you're thinking, wait a minute, only 10 times that is 32.6. So this is probably where this is coming from, and you'd be right. All right, a parsec, P-A-R-S-E-C, that stands for parallax second. And what is that? Well, it's the distance that a star must be so that it moves 1 second of arc as seen against the farther stars at each end of the Earth's orbit. And then, of course, that begs the question, what is a second of arc? It's actually pretty easy. If we note there's 360 degrees in a single circle, right? Well, each degree we say has 60 minutes of arc. And why do we call it an arc? Well, it's called an arc because it's really a small segment of the larger circle, right? It's a small segment of the larger 360 degrees. So 1 degree is 60 minutes of arc. And each minute, all right, has 60 seconds of arc. And 1 arc second then is this parallax second we're talking about. The distance a star must be so that it moves 1 second of arc over a 6-month period when we watch it here from the Earth, at one end of our orbit to the other. That is what a parsec is. 3.26 light years is that distance at which a star will move 1 second of arc in a 6-month time frame if it's in the sky. But as I said, parallax is not so easy to measure. So it has error that'll creep in over time because it might be hard to measure stars that are farther out because that movement ends up, the movement of the star will end up becoming far less than an arc second over time, over distance rather. And as we start looking at the star, that movement might be so small that it might fall within the error of the measurement. And so parallax measurements are really only good out to about 100 parsecs, which, since a parsec is 3.26 light years, 100 times 3.26, 326 light years. So about 326 light years is how far away we would actually be able to measure stellar distance using parallax. All right. Now, what does this have to do with absolute magnitude? Well, absolute magnitude puts us, and some of you that are sharper out there probably have figured this out. Absolute magnitude puts all the stars we see, we put the stars at 10 parsecs. It's the agreed upon distance at which we arbitrarily place the stars. And we try to judge their true brightness, that what we call that absolute magnitude, and then we can compare them to each other this way. Okay. Remember, the sun's absolute magnitude which is at 10 parsecs, or 32.6 light years from here, as seen from here, would be 4.77. All right. Betelgeuse absolute magnitude would be minus 5.14. So you can immediately make comparisons of the two stars by this. So this is a really, really cool thing. Now, I wanted to just mention to you that I want to pause right now because I want to ask you, Amanda, if we've got any questions, because I would actually be able to take some questions right now. And if we don't, well, that's fine too. I can just go on.
Well, we have one. It's a little political. I don't know if I want to get into it, but the first half, who owns the International Space Station? And what happens if the budget gets cut for it? I think that's an interesting question, and I don't know the answer. So
yeah, NASA operates it, and it's actually a joint project with JAXA, the Japan Space Organization, and the ESA. There's ESA modules, there's NASA modules, there's JAXA modules, there's Russian modules. Okay, Zarya is a Russian module on there. So it's actually an international consortium that's actually doing it, and NASA does manage some of the day-to-day, but so too do the Russians, okay? They also manage a piece of it. And JAXA, of course, is in full communication with their teams up there as well. So there's a number of, wrinkles. And one of the things is that, the space station doesn't have a life that's going to last forever. There's going to be a point where we may run out of money and we will have to stop funding the space station. And what will that mean? That'll mean that the space station will eventually deteriorate in its orbit and then come and fall back to the planet and fall back to Earth. What'll happen? Well, unfortunately, we saw. Yeah, it is sad, because it's really produced a lot of really interesting science. Now, if we're already on our way to the moon to make moon bases to study how we can actually take the lunar soil and turn them into fuel by taking the helium-3 from the soil, because the moon is full of helium-3. That's an isotope of helium. And helium-3 is a fusion source, a fusion source fuel. So we would actually be able to use that to power a fusion reactor. You can see that we're a ways off, though, because fusion reactors are, quite a bit farther down the track than than this. So this is a very interesting question and dilemma that we face as people that are trying to, make our way to the stars, and we may just run out of money to be able to go there in an economical way, right? So that's why privatizing space, maybe the space station will end up being sold, okay? And that's something I actually thought of the other day. Maybe we can just sell the space station to people like Elon Musk and maybe Richard Branson. Maybe the two of them would team up and say, yeah, okay, I'm going to own this module here, and you own that module over there. And Elon Musk would say, okay, I'll take this module over here, and we'll draw a line down the middle, and we don't cross over each other's side. Or something like that. I don't know. But it'd be kind of funny. But I am a big fan of privatizing space. And, I know that that sounds crazy because we think of big companies like big oil and we think, oh, they're so evil and whatever. But guess what? Big companies like that, they may have their problems, but didn't they pave the way for civilization? And yes.
And it's helping the entire world. So, I mean, just because it's only a few main countries.
Yeah, I mean, it's helping. There's so many reasons why, big oil can be bad and big oil can be good. I mean, you have to think about, the fracking question and polluting people's drinking water. Yes, there are big problems with extracting this fuel from the ground. But as I write about in my book, The Populated Universe, okay, and I'm not the only one that said this, okay, for us to generate fuel, we still have to dig up stuff that died a long time ago. We basically, and I think it was Michio Kaku who said, we still burn dead things for our fuel. And we do. Think about that. We don't use renewable sources. We still burn dead things, and we're hanging on by a thread. Okay, if that renewable, stuff came along, if we could actually, do fusion, if we could do solar, high efficiency solar, if we could do microwave transmission of energy from space, from orbiting satellites in what we would call a Dyson swarm, then that would work too. That would be a very good thing to do. And hopefully this will generate a lot of questions from folks that are listening, because I think it's important to understand where we're heading. We are going to have to leave this planet, folks. And to do that, we're going to end up having to, understand astronomy, which is why my show, okay? We're going to have to understand science a little better, which is why my show, okay? And we're going to have to understand where we can go, which is why my show. I mean, all those reasons. It's not going to happen like next Thursday, okay, or even 4 years from now. Yes, it's 5 billion years from now. So you might say, well, you're really jumping the gun there. Or you're really planning, aren't you? And like, yeah, I am planning, but I'm not planning for me. I'm planning for our future descendant. And so this is very important. So I think considering that our planet is a short-term stop for us. Yeah, we started here. Yeah, we originated here, but we haven't. We're not stuck here by any stretch. And getting interstellar, that's a topic for yet another show. But we'll touch on it all the time. I mean, to go interstellar, for instance, to go to Proxima Centauri, 4.3 light years from us. Okay, at our fastest speed we can go, it might take us about 12,000 years to get there. Well, that's no good. All right, and it's the closest star system to us. Well, to get there in a reasonable speed, well, we have to research a new technology. And we can't go faster than light, but we can circumvent it. We can go around light speed. And light speed is the speed limit in the universe, and we could go around that. We could go around it by warping space. And there's that term we've talked about before, What does that mean? Well, first you have to understand what space is. And then you have to understand what warping means. So, that's a whole show in itself, and we're going to make that a whole show probably when we talk about warp drives and how they really will look. Because we've talked about the Alcubierre drive, and that was a drive that was created by Miguel Alcubierre back in 1994, I think. And he described mathematically how we could actually warp space, what we call the fabric, quote unquote, of space. And basically, you take the diagonal pieces of paper, diagonal corners of a piece of paper, and fold them up to each other. Now, what's quicker, jumping from the 2 points nearly touching or going across the whole diagonal if it was wide open? And the answer is by folding the paper and jumping across the tiny little places where they connect. Okay, that's quicker. And that's basically what the Alcubierre drive does. It allows folding of space. And something which you might think, well, that's just Star Trek, that's not real. Well, guess what? Star Trek wasn't based in full fantasy either. It was based in some science. So this is just a maturation of some of the science concepts put forth in original science fiction. So I just think it's fantastic. Now, the Alcubierre drive will get us to Alpha Centauri. If we used it at full, I'll say full strength, it could get us there in less than a week. Believe it or not, that's a darn sight shorter than 12,000 years. But because there are some caveats with using the Alcubierre drive, meaning that like driving a car through on a highway, over time you're going to get bugs on your windshield. Well, the Alcubierre drive has this warp bubble that it's got around it, and that bubble will get covered with not bugs, but debris, high energy particles that it picks up along the way. Even though it's only going a relatively short distance, but when it stops that drive, all of those parts, all of the stuff that's on there will come off in one big, massive explosion. And that's unfortunately a problem because it means that you could get to, Proxima Centauri and you and your buddy are looking out the window saying, oh, look, there's planets, there's a whole civilization there. And as you stop your drive, ba-boom, the whole planetary system is destroyed and eliminated. And you just have to look at your buddy and say, yeah, let's just tell him that there was nothing here. Yeah, good idea. We'll just have nothing here, nothing to see here, and kind of slink away. Well, that problem has been relatively overcome in terms of lengthening the trip. If you lengthen the trip, then you can reduce and bleed off the energy and make it a little bit faster or a little slower to get there, but a little bit better by far by not simply destroying the object that you're going to. So a real trip to Alpha Centauri and the stars around Alpha Centauri system would probably be best done at about a 2 to 3 week time span. Still, that's a darn sight less than 12,000 years, and I would be okay with that, So now there's another Alcubierre variant that's coming out, and we'll, again, talk about this too. It's called the Alcubierre Froning, Froning, Froning drive, the Alcubierre Froning drive. This one covers and satisfies a number of other problems that could have come up. Like if you're traveling, at such a distance, at such a speed, you have to travel at some speed. All right. What happens if micrometeorites, come in at the speed you're traveling? They would just go right through your ship and you'd be obliterated before you even started. There's a lot of debris out in space, and a micron-sized particle, which is a very, very, very small particle, could destroy your whole starship. So how do you get around that? Well, the Froning drive actually has what's called shields. Sounds like Star Trek again, but when you actually see the design of the Alcubierre Froning drive, you see that this would mean our ship would actually have a shield around it at all times. And you wouldn't have to worry about repelling an asteroid or repelling micrometeorites or anything hitting. It's automatic. They're automatically side-slipped out of your way as you go. And that took care of a lot of the other requirements. And it also makes it easier to bleed the energy off at the end of your trip. So that's the new one that's available now, and that's going to be out soon at a drugstore near you. Just buy an Alcubierre Froning drive and send it off to the moon. Get there in about third of a second, and then you have fun. And that's a lie. That last part wouldn't happen. But I do think that it's a very cool future awaits us. Because right now, where we are in our history, again, as I've told you before, we're only about, say, 12,000 years of true written history. And maybe, if you want to count Lucy, right, Australopithecus from Olduvai Gorge, that's 4.2 million years ago. If you go all the way back to that, we're still a drop in the bucket on the cosmic time scale. And in that time, say from our written history forward, we actually can see that there are ways that we can circumvent the speed of light and actually utilize it. And all we need is energy. All we have to do is be able to get vast quantities of energy. And we can see how to do that too. Well, actually, that was the Alcubierre original. I'll talk about that. What Amanda was saying was the energy requirements to build like a warp bubble around your ship originally required something, a mass the size of Jupiter converted to energy. So that's just absolutely laughably large. And not even an advanced civilization would probably utilize something that wasteful, really. So, and of course, acquiring that energy and converting that mass, it's just impossible. How are you going to move a mass the size of Jupiter, So what they did was they reworked the shape of the Alcubierre warp bubble generator, basically. And the final result got that energy level down, that mass equivalent, they call it, down to something about the size of the Voyager spacecraft, maybe a little bigger. Now, that's like a 10 to the 27th power reduction in the energy requirement. And that made it incredible and made it something that people would really, really like to follow through with. And that's why, Dr. White at NASA now has a lab that's investigating the Alcubierre Froning drive, because it satisfies all the requirements and it allows us to do this with a reasonable energy. Now, the first ships to go to Alpha Centauri are not going to be big starships with lots of people going, "Ooh, look at the pretty stars." Okay, they're probably going to be what are called nano ships. They're going to be tiny little ships, maybe the size of a marble, or maybe the size of a Coke bottle, or something like that. But it'll be something small to prove the concept. And we're going to do a lot of that, and probably for 50 to 100 years worth of testing before we actually do that and travel out there. But this will be something that I think will be, it'll be our legacy that we leave behind, is the research that we do. And now, just to talk about an interstellar interloper, just to close out the show here, I want to share something with you, okay, about a special little interstellar asteroid that visited us, and it was discovered on October 19th of 2017, and it was called
the operative word.
Yeah, well, in a sense, right? It was an asteroid called Oumuamua. Now that means messenger in Hawaiian. Actually, messenger from afar arriving first is what it actually means. And it was originally thought to be a comet because it had a really strange shape. It was 10 times longer than it was wide. We don't have anything like that in our solar system other than comets. If you look at them kind of roughly from a distance, they might appear like they're longer than they are wide because of the stuff they're trailing behind them. But the fact is, it was an elongated asteroid, a rock. And it came in at such an angle that it couldn't possibly have been in our asteroid belt because it was far above that asteroid belt. And it literally entered our solar system at 196,000 miles per hour. Okay, that's 87.3 kilometers per second. Okay, so that's really fast. So there's nothing like that in our solar system so far, as much as we can tell. And it's about a quarter mile long, but only about 130 feet in diameter. Absolutely incredible how that could actually exist. Now, it has a surface that's, it reminds you of, it's actually like an interstellar shard of rock, and it appears to have wandered for several 100 million years out in interstellar space. It has no water or ice. It's really parched, and its surface is red, reddish, and that happens because of radiation, cosmic rays, bombardment by radiation over time. And this is why Oumuamua was so interesting, because it is the first true interstellar asteroid that we could track and see. And that was just cool. Now, you may say, wow, that's cool, once in a lifetime event. Actually not. There's about one asteroid like that per year that passes through our solar system, and that's actually typical. However, Oumuamua was one that we actually got to see, and we actually could track. And at the speed it was moving, it was just incredible. Now, on its way out of our solar system, Oumuamua was slowed down a little bit by our sun as it was leaving. It was being pulled by our sun. And so it slowed down from 196,000 miles per hour to 87,500 miles an hour. Oh, see, that's a lot slower, right? Okay. No asteroids moving that fast, I can tell you that. not in our system. So that all said, this particular asteroid came from the direction of where the star Vega is now. But see, Vega wasn't there for much of this thing's trip, okay? And so when it came from Vega, Vega wasn't there in the sky. There were other stars there. So we don't know how an asteroid like this could have been formed and then ejected from its solar system or its star system and then made its way through interstellar space to us. It's incredible. And Oumuamua is heading for the constellation of Pegasus right now, the winged horse. So I think that's a real fitting way to end tonight. So we will see you next week, and I hope you'll join us. So remember, keep looking up, except when you're driving, and I hope you have a really good time. All right. See you later.
Great week, everybody.
Good night, folks.